In this lecture we discuss symbolic power of prime ideals. So let P be a prime ideal in some ring R and say n is a natural number which is non-zero. So then the following ideal is called the nth symbolic power of this prime ideal P. So we write here n in braces like this. So P to the n in braces is just all the elements A of the ring are such that A times B lies in P to the n for some B which lies in R minus P. So this B does not lie in the prime ideal P. So notice that if you take this prime ideal out of the ring R, what you get is a multiplicatively closed set S, and often we localize with respect to this set S. So here is a lemma for symbolic powers. So P to the n, this is contained within P to the symbolic power of n, which is in turn contained within the prime ideal P. So this is part A. So let us first prove this part A. So for part A, the first inclusion, so Pn is obviously contained within the symbolic power of P to the n by just taking B as 1. So if you take B as 1, you take any A in R, then A will be in Pn. So you start with A in Pn and then you take B as 1. This A will again lie here in Pn. So this condition is satisfied. So first inclusion is obvious if you take B as 1. Now we want to consider this second inclusion here. So for the second part, you start with some A here which lies in P to the symbolic power of n. So A lies in P to the symbolic power of n. So by this definition, that means A times B lies in P to the n, where B lies in the complement of the prime ideal. So AB lies in P to the n, which in turn lies within P, because P to the n, P is a prime ideal, you take its nth power, it will still lie within P. And B, as we just said, lies in the complement of P, but P is a prime ideal, so it has to be the case that A lies in P, because AB lies within P, B does not lie within the prime ideal P, so it has to be the case that A lies within the prime ideal P, since P is prime. So we start with A in P to the symbolic power of n, and we ended up with A lies within prime ideal P. So A is done. Now part B, P to the symbolic power of n is P primary. So to show that it is P primary, the first thing we do is we show that the radical of P to the n is P. So what we do is you copy this thing right here and start taking radicals. So you have this thing, you take this radical here, you write radical P to the symbolic power of n. This P here, you take radical of P here. So this P to the n here, you take radical of P to the n here. So we have copied this, just taken radicals, and radicals preserve this inclusion from here. Now since P is prime ideal, radical of P would be P. Radical of Pn would be same as radical of P, which is P, because again P is prime ideal. So you have P here, you have P here, so we have shown radical of P to the n is P. So that was the first part of showing that P to the symbolic power of n is P primary. We had to show that radical of P to the symbolic power of n is P. So now we show that P to the symbolic power of n is P primary. So we have already shown that radical of P to the symbolic power of n is P, as there is P on both sides of the inclusion. Now we have to show that it is P primary. So what we want to do is we start with A times P lies in the symbolic power of P to the n. So to show that this is P primary, we have to show either this A lies within the symbolic power here, or B lies within the underlying prime ideal P. So our strategy is we start from here, we will say that this is not in P. So we will assume if this is not in P, then it has to be the case that A lies within symbolic power of Pn, and that will finish the proof. So we'll start from here and we have to end up right here. So if AB lies within P to the symbolic power of n, then you have to use this definition. So there is some x, so that ABX lies in P to the n. So ABX lies in P to the n, where this x also lies within R minus P, or we are setting R minus P equal to the multiplicatively closed set S. So x lies within our multiplicatively closed set S, which is equal to R minus P. Now say B does not lie within radical of P to the symbolic power of N, which is P. So B does not lie within P. So if B does not lie within P, then it lies in the complement of P. So B lies in the complement of P. So B lies within this multiplicatively closed set S again. So we have B lies within the multiplicatively closed set S, which is R minus P. X also lies in R minus P, since this is multiplicatively closed set S. So you have Bx lies within multiplicatively closed set S, or Bx does not lie within P, which is a prime ideal. So since Bx does not lie within P, now we have this ABx. This Bx lies within S. So our definition is such that ABx lies within Pn. So we start with A times B lies in the P to the symbolic power of N. So this A therefore has to lie within P to the symbolic power of N. So we are just following the definition here. So this Pn consists of all A that if you multiply by something which lies in this multiplicatively closed set S, which is complement of prime ideal, then these A's lie in Pn, and that's what we are following here. So therefore that's what we wanted to show, and therefore this P to the symbolic power of N is P primary. So now we want to show this part C, this P to the symbolic power of N in this localized ring at prime ideal P is equal to P to the power of N, this ideal in the ring R localized at P. So both of these rings are localized at our prime ideal P. Obviously localization is with respect to this multiplicatively closed set S, which is R minus the prime ideal P. So first is that this inclusion we are just copying from here. So this inclusion we copy right here. So this inclusion implies that we have this inclusion. So Pn Rp contains Pn R this P. So the symbolic power of Pn, this ideal would contain this thing. So this inclusion is obvious, just follows from here. In the other direction, we have to show that this P to the symbolic power of N in the localized ring is contained within P to the power of N in the localized ring. So opposite directions. If both of them hold, then you have equality. So for this, what we will start with is we will say B over S lies in this P to the symbolic power of N, this ideal, and we will end up showing that this B over S here will lie in this part, P to the N, and that will solve the problem. We start with an element in here and we'll show that element lies here. So if B over S lies in this ring, because this is a localized ring, S lies within the multiplicatively closed set R minus P. So this is capital S. So S lies in this set. So if this is true, then BC is element of Pn for some S and C in R minus P. So this just follows from the definition here. You are saying that some fraction is here now, because you have this Rp here, this fraction lies in here, but you have to multiply with something so that it gets into P to the N, and we are saying there is some C you can multiply with so that you will end up in Pn. So this has to follow. So for some S and C in our multiplicatively closed set S, which is complement of the prime ideal. So basically what we are saying is B over S is now equal to this BC over SC. So this BC lies in P to the N, so numerator, and SC lies in the denominator, because we are picking up S and C both in the complement of prime ideal P. So this lies in the fraction here. So so this holds. So therefore we have shown this inclusion, we have shown this inclusion here, so you have an equality here.